Hi, in today's video, I'll be giving a short introduction on linear programming using the Simplex method and how you can do linear programming on Excel. Let's start with what is linear programming. Linear programming is the process of optimizing the value, meaning you find the max or the mean of a given linear equation given a set of constraints. Let's take a look at a simple two-variable example to understand what do I mean. So we want to optimize the following function z equals to 180x plus 200y, and this function we'll call it the objective function. Below is our constraints: 5x plus 4y less than or equals to 80, 10x plus 20y less than or equals to 200, x greater than 0 and y greater than 0. Why we are using a two-variable example is because it allows us to visualize from the graph what is happening. So when we plot the graph, we have the line 5x plus 4y equals to 80 and the line 10x plus 20y equals to 200, and they intersect at this point, which is 13.3, 3.33. Now, based on the constraints, our x and y can only lie in this region over here, and then it must be below this curve and this line. And so when we realize and we plot it out, this will become our feasible region, and these are the points that the x and y can take value in. Now, what we want to do is we treat this objective function as just a curve that can vary. So in this case, for example, like this curve, this is 180x plus 200y equals to 0, and we see that it touches the feasible region, means our x and y can take values so that it can reach this value of z equals to 0. But then we start to realize that we can actually shift this line further up, and you see that it passes through this vertex now. This vertex is the 0, 20 point, where x is 0 and y is 20, and it increases the objective function value. Now, this means that we are maximizing or increasing the value of z, and so what we want to do is to increase the value of z so that it still lies within the feasible region, but there are still points where x and y satisfy that equation. And so we can realize that over here we can still increase it, and then we reach a point where we increase it any further, it will lie outside the feasible region, and so we get a good intuition that this vertex over there is where it maximizes the objective function. Or another way, if you do not trust this way, is that you can just find the value over here at all the vertexes, and then you calculate each one for the value at using the objective function, and then you just choose the maximum. But you can actually intuitively guess that this vertex is the maximum point, and so you calculate the objective function at this vertex and you'll result in the maximum, which is going to be 3067 for the point 13.3, 3.33. This graphical approach will be left for you to do an example to see it out, but now you get an intuition on how do we maximize this function. But it is hard to realize where are all these vertices when you're at higher dimensions, and so mathematicians have come up with a way to convey what we are trying to do in a step-by-step procedure. This is known as the Simplex Algorithm. But there are some things to note about the Simplex Algorithm. One thing is that we are always trying to maximize the function, and so while the graphical approach can tell us the minimum over here, like 0, if we want to maximize and minimize any function using the Simplex Algorithm, you just take the negative of it. It is that simple. And for all the constraints, it must always be less than or equals to. And so if you have a constraint that is greater than, you just need to take the negative of it, and then you can apply this Simplex algorithm. So let's go on to the technical parts of the simplex algorithm. Using the same example, we write down all the objective functions and constraints into a table as follows. But for our constraints now, since they are in inequality form, we need to convert it to equality form by introducing S1 and S2. These are known as the slack variables. Now we write everything into a table where we have all our variables known, x, y, s1, s2 and z, and these are the coefficients for each constraint. And then at our last row, we write the objective function again. Now, based on the last row, we choose the one with the smallest value. In our case, the negative 200. And we call this the pivot column. So y is our pivot column. And what we need to do now is reduce the coefficients in y to be 1. After reducing each to 1, by dividing it by 4 here and dividing it by 20 below, we see which values on the right hand most is smaller. In this case, it's the second row because it's 10 is smaller than 20. And so this row now we call it the pivot row. And then this point in y is now called the pivot point. We want to keep this point 1 and reduce this and the one below to 0, which is what we do as shown in table 3. How we do this is we just take the first row minus away the second row, like here. So 5 over 4 minus half is 3 over 4. And then you do the same for this rest, and you get the values here, where in the y column now is 0. Similarly, for the last row, you do this following, and this becomes 0. Now, how do we know whether it's the optimum solution? The optimum solution must ensure that all the variables here are not negative, the coefficients. And so because there is still a negative here, we repeat the steps again. So because this negative is now the smallest value, this becomes our new pivot column. And then reducing both to 1, we see that 40 over 3 is now smaller than 20, and so this is our pivot row. This is our pivot point, and now we just reduce them to 0, 0. After doing so, we reach a point where these are all positive values. And then we now know that because the slack variables were not originally there, this can be treated as 0, and so z equals, with a coefficient of 1, means z equals to this value over here on the right is our maximum value. And you can see that it actually tallies with what we have found in the graphical approach. And so when all these values are now positive or non-negative, we choose this x coefficient, so 1x equals to 40 over 3 as the value that maximizes the objective function, and in our case here is 2y equals to 20 over 3 that maximizes the objective function. And so x equals to 40 over 3 will be where the maximum value of the objective function occurs when y is 10 over 3. Remember that here is 2y, so 2y is 20 over 3, and so when you reduce it to y is 10 over 3. And you can see now that all of these are actually coinciding and agrees with what we have done for the graphical approach. And so this is how to do the simplex algorithm to do linear programming and maximize an objective function that you want. Well, this is quite tedious. There is actually a way to do this in Excel, which is already built in. And so we are doing this manually first to understand how does this all work, and that it actually makes sense and you get a sense of what is happening graphically. And so now let's move on to the Excel functions. So in Excel, what we need to do is to create this sum product rule over here. So this is our objective function, where it uses these coefficients and the value of x and 1, which we want to just put 0, 0 always first initially because you don't know what it is. Then our constraints are as follows, 5 and 4, and then this over here will be where we place our constraint, which is the sum product. And similarly for the below one, our constraint 2, which is 10x plus 20y, the sum product is less than or equals to the 200. So how do we do this linear programming? We just need to go to the top right and click solver. So when you click onto solver, we just set our objective, which is over here. You click it, you set it, we want to maximize it, and now what cells can we change? We want to change B8 and C8 because that's x1 and x2, or in our case x and y. Then we set the constraints D11 to be less than F11. So how we can do that is by adding it over here. So D11 is now less than F11. So when you go into here, I already typed in D11 less than F11. You can also delete it if you want, which I delete first. And so when I add it now, I click into this. So I add it, I click into this, I click here, and the constraint part, I click here. Thank you. So I add another one again, so cell reference here, less than the constraint which is here. So this is how I will add the constraints in, and then we choose the method as the simplex linear programming method, and then we just click solve. And then the values will just appear over here. So as you can see, they tally with our example using the manual approach, and this is how you can do so in Excel. Thank you for listening, and I hope you have enjoyed the video. Please like, share and subscribe, and you have any question, please leave them in the comments section down below. Thank you.